All right, should I start now?
We probably wait for 5 minutes just for people to come in.
Okay.
Yeah. I think we have a very good number here on Zoom. So I'd like just to say hello, everyone, and welcome to this training session held by young members group of I-Structure Regional Group, UAE. And we're starting in 3 minutes.
I think we can start now, right? Okay, I think that's a yes. Good evening, everyone. I hope you're doing great today. Welcome to our first software workshop for this year. Let me introduce myself first. I am Rukaya. I'm a graduate civil engineer at Jacobs, and I am the graduate representative in the I-Structure Young Members Group in the UAE. So our speaker for today's event is Dr. Mustafa Batikha, who is an assistant professor at Heriot-Watt University, Dubai campus. He got his bachelor and master's degrees in civil engineering from Damascus University, and in 2008, he gained his PhD from Edinburgh University in the UK. So Dr. Mustafa worked as a full-time lecturer for undergraduate and postgraduate students at many universities like Damascus University, Edinburgh University, Yarmouk Private University, until today, where he's working at Heriot-Watt University. Also, Dr. Mustafa has guided research work individually and through the supervision of master's and PhD students in different structural engineering fields. Coming to consultancy work, he has completed many high standard projects from 1994 until the present time. So in today's event, in the first hour, Dr. Mustafa will be discussing the basic principles and the things we need to know before using any structural design software. Then he will introduce us to SAP2000 software, followed by SAP tutorials. So please make sure that your software is open and ready to be used. Also bear in mind that you can send us any questions at any time during the event, and we will address them later on. And without further ado, I'll hand it over to Dr. Mustafa to discuss the basic principles before using a software. So, Doctor, the floor is yours.
Okay, thank you very much, Ruqayya. I'm going just to share my screen first before I forget. So here is my screen, and I hope that all of you can see my screen. Okay, thank you, Ruqayya, and thanks for iStructE for offering me this opportunity to do this workshop. And in this workshop, I'm going to talk about that using structural software tools in general. And we are going to talk about SAP2000 as an application or as an example of using this software. So thank you, Ruqayya, because you saved time for me to introduce myself. Yes, so you said a lot of work about me. And actually, if you want to know more about me, you can go to my LinkedIn shown in this screen. And I have a full CV about my experience. And as well, you can see my email. So please, after this session or after this workshop, please don't hesitate to contact me if you have any inquiry. But before we move forward, I would like to introduce our new Heriot Watt Dubai campus, which is fabulous as you see here. So as well, I'm asking you to go there and have a look from inside because it's really fabulous. So let's start our workshop. So as Ruqayya presented here, so our workshop is a combination of two parts. Part one, I'm going to talk about basic knowledge that you need to know before using any structural software. Without this knowledge, you cannot go to any structural software because you don't know what the result at the end you are going to obtain. And maybe this will be false result. And you know that in structural engineering, any mistake can cause a disaster. And in second part, I'm going to use SAP2000 as a software, as a common software to apply this basic knowledge I'm going to provide today. So let's start with the basic knowledge. As all of you know that the structural system means that you have a structural element and support, and this structural system has loads applied to the structural element. When we are talking about structural element, we are talking about two things here, material and dimension. So you need this three part to be ready for your software. So you need structural element, which mean material and dimension. You need actions, load, and you need support. The common applied load, we have two types of common applied load we use in structural engineering. We have gravity load, we have lateral load. In gravity load, for example, we have dead load coming from cladding, from self-weight, from life load, imposed load, snow load, as seen here in this photo. As well, the common lateral load comes from wind load, which is external pressure applied to our building, and seismic load. The seismic load is ground movement, but because of the dynamic nature of this ground movement, we transfer this ground movement to equivalent force applied to our building. But actually the seismic load, actually it's ground movement. It's not force applied to building. how we deal with this force. When you apply this force to any structural element, you will have a deformation. So the most simple deformation is like, for example, you have axial deformation, like here you may have compression. So the element shrink as seen here. You can represent this shrinkage by compression force. And or the element itself may expand and stretch like this. And you can represent this deformation as you have a tension force. As well, some structural element will have bending deformation. In bending deformation, you have two fibers, as we know. One will shrink, which means that it has a compression force, and the another fiber expand and it has like tension force. The post action will be at the same time during the bending deformation, both action, compression and expansion. At each side, you see that I have compression and tension or couple of force, and this couple of force will cause what we call it bending moment. The shear force as seen here in this, have a look how the shear deformation is, and it can be represented by two opposite force. This deformation will cause a very important parameter we deal with. It's the strain. The strain is the deformation over the original length, and have a look, the strain is dimensionless parameter. And from here, the importance of this parameter comes from. When you combine these strains with elastic modulus, and the elastic modulus here represents the material. So any material, according to the type of this material, has an elastic modulus. So when you combine the strain with the elastic modulus, you obtain a stress. When you take this stress and you combine this stress with the properties of the section, like for example, when you take this stress times the area, you obtain a force. Because of that, we call this force stress resultance. That what we call it internal force, but actually it comes from the stress. Here we have many types of force. We have compression, we have tension, which are axial force. We have bending, torsion, we have shear. When you combine this internal force or stress resultant again with the property of the section, here is the most famous section, you obtain stresses. The stress, we have two types of stress. We have normal stress, as seen, it's axial stress. It's come from axial stress here, pure axial stress, N over A, or bending stress, which is the bending moment over the elastic modulus. So this provides me normal stress. We have another type of stress, which is shear stress. The shear stress comes from two types of forces. It comes from shear force or torsion. The torsion as well causes a shear stress. But actually, not these stresses cause the failure of the structural element. The combination of these stresses provide us something we call it principal stress. So if you want to ask yourself how any element fell, structural system fell, you need to check the principal stress. Have a look at the formula of the principal stress. You can see that this formula is a combination between axial stress and shear stress. Because of that, these principal stress are higher than the stress, each stress, like normal stress or shear stress. And because of that, for example, if I want to check the failure in concrete, or I want to see how the concrete cracked, I order the software to provide me the principal stress. And we will see now, after this part one, we will see that how the principal stress guide me to the crack in concrete. This principal stress gave me the famous Moore circle, which is very important. You see that in Moore circle, we have two unique points, sigma 1, which is the maximum axial stress, and sigma 2, which is the minimum axial stress. You see that these two stresses, which are, for example, sigma 1 is the maximum stress you can apply to that element. And sigma 2 is the most minimum stress you can apply to that element. You see that these two elements, sigma 1 and sigma 2, are corresponding to shear stress equal to 0. Why actually we select these two stresses? We select these two stresses, I mean, at the position of shear stress equal to 0 to compare with the experiment. For example, if you do compression for concrete, you take a cylinder and you do a compression for this cylinder. For this cylinder, you apply pure axial stress, not combined with shear stress. So because of that, you need theoretically stress with 0 shear stress, and here is the stress. So when you compare your experiment with the theory, you need to take this principal stress where the shear stress is 0. We have other stresses you may see in any software, Van Mises and Tresca. And you may ask yourself, what is this Van Mises, what Tresca? Actually, Van Mises and Tresca represent here the yield of steel. So it's just for steel material to check if your steel material yield or not. And have a look at Van Mises stress. It's a combination of the principal stress. Have a look, sigma 1 and sigma 2 on Moore circle, where tau again is 0. So it's bigger than, actually, Van Mises is bigger than sigma 1 and sigma 2. And again, the aim of this stress is to compare the experimental test that you are doing on steel sample with the theory to check the yield of the steel. Tresca is a conservative of Van Mises, is conservative limit of Van Mises, but you don't need to use it. The general one is Van Mises, so you don't need to use Tresca. But you need to know that both stresses are to check the yield of steel, but you can use Van Mises with any, offered by any software. Now, what the aim of the structural design? We always in the structural design look at two criteria. First of all, the strength. So we need to make sure that the material doesn't fall under a certain stress or under principal stress. Let's say principal stress, because principal stress is a combination again between axial stress and shear stress, and it's bigger than any isolated stress. And the stiffness, we need always to make sure that no much deformation. You may have deformation, but you don't have failure, okay, but this deformation will not allow you to do other things, like, for example, this deformation. If you have much deformation, this deformation will cause that you cannot install finishing, for example, or the people doesn't feel comfortable. So, for example, if the slab is too thin and it deforms, so it shakes under movement. So this will cause uncomfortable life for the residents. So you need to check as well that the deformation is within a limit. Now, before you start, after this introduction, before you start doing, or use any software, you need to collect the structural analysis data. So you need to make sure that all these data are available with you before you start modeling or using any software. First of all, what is the type of element? Second, what is the dimension? When I'm talking about dimension, I'm talking about 3D dimension. I'm talking about section and length. So 3D, because the section has 2 dimensions. You need to know what is the insert of the material behavior. You need to know what is the support for that structural system you are going to model. And finally, how you are going to apply the load. If we go one by one, so here is what I'm saying, that this is the data you need to collect before you use any software. If I start to talk about the type of element, in nature, the element is a 3D element, 3-dimension element. In the 3D modeling, you have like this cube element, like for example, or let's say 6 faces element, or you have like this element, this 3D element, which has 5 faces element. But using this element, I mean 3D element in modeling, is very complicated and it takes time in analysis. It takes too much time in analysis. So because of that, we try to simplify this element to more simple element, like to transfer this 3D element to 2D element. How we do that? How, like for example, some element, like for example, like slab. The thickness of the slab is too small in comparison with other dimension, with the length of the slab in 2 directions. So because of that, why we deal with the thickness? So we can transfer this 3D element as a slab to 2D element, and we just model the face of the slab. So no needed to model the thickness. As well, in some element, you can transfer this 2D element to the most easy element in modeling, which is 2-node element. 2-node element or linear element. It's the most easy element for modeling. For example, have a look at this element. You can see that the section of this element, the dimension of the section, are too small in comparison with the length of this element. It's like line. It's like you are drawing line. So why don't we model this element as linear element or 2-node element? This will make your analysis fast and doesn't make that much different if you make your element as 3D or 2D. But it's some accuracy. But this will make your element analysis time fast. So you need actually to know what is the type of your element. Can you do it as 2-node element? Can you do it as 2D element? Because do it as a 3D element is more complex. For 2D element, we have 2 types of element actually you may face. First type is plane stress, and that type comes for thin body, like as the slab example. So I said that the thickness of the slab is too small in comparison with the other dimension of the slab. And because of that, when you study slab, you find the bending moment in 2 directions, and you find the stress caused by this bending moment in 2 directions only. Because of that, we said that this slab is stress plane, which means that the stress are only in plane, whereas sigma x equal to 0. But you have deformation because you applied the load out of this plane, so you will have out of plane deformation. Here, many examples of plane stress, example like slab, shear walls, another part, membrane domes, like have a look, like this Sydney Opera or Mosque Dome or Cathedral Dome. We have another type of element of 2D element, it's a plane strain or thick body. We call it thick body. Have a look at, we use this element, for example, again, using this element will save time for you. And I mean the analysis will be fast. So for example, we use this element to model soils, to model earth-filled dams. Have a look at these dams. You have here the plane of the dams, but the thickness of this dams is in Z direction, here in this direction is so high. So what we said that these dams will offer a deformation in two directions, X and Y, but in Z direction, the displacement is 0. But you have stress in Z direction. So that's what we call it plane strains, and many software offer like plane strain element to be used, I mean, instead of you do 3D dimension element. When we are talking about linear element, you can see a lot of example in our building about linear element. Like for example, here in building, you have beams as line element. Have a look how this beam is long in comparison with the section, the column as well. The length of the column is long in comparison of its section. Have a look at this here, these arches here. These are the length of this arch is so long in comparison with its dimension. But the slab between two arches here, okay, you see that it's 2D element. Why? Because the thickness of the slab is here is too small in comparison with the other dimension, the length and the width. You see here the bracing element, you see here the truss element, all this like you are looking at line element. You see here that this amazing stairs here, how it's full of truss and truss element and line element. Material, the material behavior. Any material has two regions or two zones, elastic zone and inelastic zone. So that's the norm. Any material has the same behavior. After the elastic zone, the material may act into two different directions. It could be a ductile material, which means that this material can sustain long deformation before it fell, or this material after the elastic zone may have a bit brittle collapse or sudden collapse. So at that time, we classify this material as brittle material. As an example, have a look at the behavior of the concrete. The behavior of the concrete is brittle because after it reaches the maximum stress here, the concrete reaches the maximum stress, we have sudden collapse. And have a look, whenever you increase the strength of the concrete, the brittle collapse will be more and more. The ductile material, steel material, is a ductile material because, have a look, it has long deformation before the steel fell. Now, it's a condition, like, for example, in some design to confirm that your material is ductile. Like, for example, in seismic design, it's not acceptable at all that you use brittle material because you don't, in the ductile material, you give warning for the failure. So it's assumed that you obtain warning before the failure. So you do something, you run, for example, or you do strengthening before the failure completed. And sometimes the ductile material offer you, like after the disaster, like after the seismic, the structure stay as it is, but you need to repair, to do some repair. So the ductile material offer you economic after the disaster. It's economic design after the disaster. Now, if you have brittle material and you have ductile material, you can combine them together and you obtain like semi-ductile material. Like, for example, have a look at this curve. It's a curve for reinforced concrete element under bending, or as well here, the steel confined concrete. You see that before you add steel, you see that the failure of a cylinder of concrete is very brittle. But after you add steel, here you confine the concrete by steel. So you see how you have long deformation before the failure, and the steel provide more strength and more ductility. So you need to know what is the material you are dealing with and what is the curve of this material. Support, we have many types of support in software. We have like pin support where no deformation in X or Y. We have roller support where you have this support restrain a point against one movement direction, or you have fixed support like here, so no movement and no rotation. But between this support, you may have spring support. So that's the real, actually the reality of the support is spring support. Why? Because in reality, you have a little displacement, but this spring has a stiffness, which is the force applied to this support over the deformation. So for example, in the reality, the column itself is not fixed support because you have deformation in the column, but because this deformation is too small, so when you consider the stiffness of that column, which is the force over the deformation is too small. So because of that, the stiffness is infinity, and because of that, we say that we don't have movement here below the that beam. If it's supported to column, so we add support. But actually, the real behavior is a spring. But in some case, for example, when you want to study, in some case, when you want to study like foundation supported by soil, in some cases, we model the soil as spring. And this will give economic, by the way, in design, and will provide you the real behavior of that foundation supported by that soil. So that's, advanced study. The loading applied, you have two types of loading to apply to your structure. You have static load and you have dynamic load. You see the difference between the equation between the static load and the dynamic load. In the dynamic load, you see that there is two terms appear here. Mass time acceleration and damping times velocity plus stiffness time deformation, which provide us the final force. And you see here in static load, we don't use the acceleration, we don't use the velocity, we use only the stiffness time deformation. And the stiffness, as seen here, equal to the force over the deformation. To represent the behavior of any structure under this force, you see that you need to draw the relationship between the deformation and force. You see the behavior of this, the structure. So it presents like elastic behavior, then plastic behavior. And you see that this is the stiffness. Here, the slope of the elastic region is, we call it the stiffness. And here, we have many types of the stiffness. We have axial stiffness, we have bending stiffness. In the cyclic load, we apply the load toward and backward. So you see that it goes, the load goes in two directions. The envelope of this load provide me exactly like the shape of the pushover analysis. In the dynamic, it's different story. Because of that, we rarely to cover the dynamic load for UG student. We use the dynamic load for MSc courses that we offer, like one of the course I offer for MSc student is tall building, and the dynamic will be clearly shown during the wind load and the seismic load. The type of analysis itself is very important. We have actually three types of analysis. We have linear elastic analysis, you have materially nonlinear analysis, you have geometrically materially nonlinear analysis. If you know what is the materially linear analysis and geometrically and materially nonlinear analysis, you will know what is the linear elastic analysis. So in materially nonlinear analysis, you provide the software the full behavior of the material. The material always, we represent the material as a curve, a relationship between strain and stress. So you see here in this curve, if you give the software the full curve, which is the elastic zone and inelastic zone. So this means that you order the software to deal with the nonlinearity of the material. The geometrically, it's like this structure will have big deformation for a reason. This big deformation will add extra bending moment to the bending moment you have from load. And this extra bending moment need to be taken into consideration, because you add extra bending moment, you need to notice. For example, if you have buckling, have a look. If your element has a buckling, so it will have deformation. This deformation, the load times delta will cause what we call it P delta. Its extra moment come from buckling. Now, these two types of analysis are complicated using the software. So you need to be expert and you need to do trial before you use these two types of analysis. So now, for example, because of that, or what I want to say, because of that, sometimes the code offer you something to avoid doing this analysis. Like, for example, they give you a limit for the deformation. So if your stiffness satisfies that limit, they are telling you, okay, no needed anymore to do like geometrically analysis. And as well for the material, like most engineers don't prefer to go behind the elastic zone to offer their structure safety factor. So because of that, most of engineers used usually linear elastic analysis. But the linear elastic analysis, just I want to tell you, it's very good for inertial design. So when you do inertial design, you can use linear elastic analysis to confirm the safety of your structure. But sometimes you need to confirm the economic design, okay? Sometimes when you change the load applied to the building, and you need to take a decision about, do you need to do strengthening to your building? So at that time, linear elastic analysis is not enough. You need to go to do materially nonlinear analysis or geometrically and materially nonlinear analysis to take the appropriate decision regarding, do you need to do strengthening? And as well when you do economic design. But again, this higher analysis, you need to be aware how you apply them. Because of that, we are offering these two analyses for research, for when our student like doing dissertation research or PhD, MSc course. So because you need to have background about these two types of analysis. Okay, here I finish. I end with part 2, and your questions are so welcome.
Thank you so much, Dr. Mustafa. That was very informative. That took
Thank
me
you.
back to university lectures.
Yeah.
Guys, if you have any questions, please send them. People that are watching us on YouTube, you can type on your questions as well. I think there are no questions for now. Shall we take a, oh, we have one. So Hassanuddin is asking, can we know about the pushover analysis?
Yeah, yeah, sure. I can give you like an idea about. So here is the pushover analysis. I don't know if you let me share my screen again. Sorry. You can see my screen, yeah?
Okay.
Yeah, can you see my screen?
No, sir.
Okay, so pushover analysis is when you take, I mean, first of all, when you are using pushover analysis, you need to apply either materially nonlinear analysis or geometrically and materially nonlinear analysis. So you cannot do pushover analysis if you are using linear elastic analysis. What do I mean? I mean that when you are using pushover analysis, you need to provide the software the full behavior of the material you have, the strain and stress. So the pushover analysis is very easy, is that you take that element. For example, if you have a beam, for example, and you have a concentrated load at the midspan.
Dr. Mustafa, I'm sorry to interrupt, but we can't see your screen.
You cannot see my screen. Sorry, just a second. I'm not sure. Just yeah, just a second. Sorry. Share screen. Okay, share. It's fine now.
Yes.
Okay. So again, sorry. So again, when you are talking about pushover analysis, you need to provide the software, the materially nonlinear behavior of the material. So you need to provide the full behavior of the material, the relationship between the strain and stress. And you see that this relationship will have elastic zone and inelastic zone. So you need to provide this behavior. So as an example of this pushover analysis is a beam, like for example, take a simply supported beam and apply a concentrated load at the midspan. Okay, if you are doing elastic linear analysis, so you will keep pushing. You keep increasing this load, and you will notice that no failure under this load. But if you provide the nonlinear behavior of the material, so you may have like this here, this relationship between the displacement below the load and the load applied to this beam. So you see here that the load start increasing until it reach a certain point where the load fell, or like for example, if you have steel material, so the steel yield and you see that it goes like steel behavior. That's what we call it plastic hinge. So you have a long deformation and under constant load. Have a look, under constant load. So this is the pushover analysis, so that you keep applying, increasing the load, you keep increasing the load until failure. I hope this answers your question.
We have another question. Basil is asking, what's the difference between time history and response spectrum analysis in the dynamic nonlinear analysis?
Yes, the time history is the real analysis. Actually, all this issue, we explain it for master student. For master student that they are doing, like, for example, I have a course, as I said, like design and analysis of tall buildings. So we explain all this issue for master student. The difference that the time history is the real behavior, is the real, like, for example, you draw a relationship between time and acceleration, a relationship between time and ground movement, a relationship between time and velocity. So it's the real behavior of the building. But the response spectrum is the maximum response of the building. So using response spectrum for design is safe, more safe. Why? Because you are taking the maximum response of your structure and you design your structure under this maximum response. But in time history, you are using the true situation, okay? And because of that, the time history, the design using time history is more economic, okay? And where is the issue here? The issue here is when you want to check, do you need to strengthen your structure or not? This is the decision you need to make. Okay, if you use response spectrum, you may find yourself that, yes, I need to strengthen my structure. Why? Because in response spectrum, you apply the maximum response or the maximum acceleration, the maximum displacement, okay, to that structure. But in time history, you take the earthquake as it is, the real action. So your structure may not fail until under the real action. Yeah.
Thank you for that. We have another question from Mohammed. He's asking, if I apply normal load on stress element, will there be existence of shear stresses on various angles of elements?
Sorry, say again.
He's asking, if I apply normal load on stress element, will there be existence of shear stresses on various angles of element?
You mean when you apply axial load to axial element? I mean to an element axial load?
He actually can unmute himself and ask his question.
Yeah, but yeah, let me just a moment go to the. Yeah. So I couldn't understand. I mean, so you apply, what I understand that you apply axial force to an element. Will there be shear stress? Is that what you mean? Is that?
Muhammad Abdul Muqtadir, if you hear us, you can unmute yourself. Okay, I
Hello.
think, yeah, we can hear you.
Yes, ma'am. I'm talking about the axial loading.
Yes, axial load. Yes, okay. So you apply axial load to element, like you apply axial load to column or something?
Axial load to beam, sir.
Axial load to beam. Yeah, so yeah, have a look here. When you apply axial load to beam, okay, you will not have shear force unless you have buckling, okay? Why? Because the buckling will cause a bending moment. As I explain here, I'm not sure if I'm still sharing my screen. Yeah,
Yes, sir, you are.
yeah, but let me, okay. So here, this is the axial force, okay? This is example of the axial force here. So, and this is a beam actually. Don't consider this as a column. Consider it as a beam and you apply axial force. So you see that without buckling, the shear force and bending moment to this element is zero. But here, if you have buckling here at this element, you will have at this time, you will have extra bending moment. And at that time, because you have bending moment, so you will have a shear force. You will have reaction. You will have lateral reaction here because of this extra bending moment. So at that time, yes, you will have shear force. If you have buckling.
Thank you, sir.
Yeah.
Last question is from Mohammed Faisal. He's saying, my question is regarding which mentioned earlier about dams. It is a massive structure which have a measurable dimensions in 3D. So if we modeled it as a plane element, can we neglect the third dimension stresses and deformations? And by third dimension, he means the width of the dam.
Yes, sure. There is a special element in software. There is a special element. The software use like, I mean, different name for that element. It's a plane strain element. So if you model this face here as seen here, if you model this face and you give order to the software that this face is plane strain, so the software itself will understand that this is a plane strain because of this thickness here, okay? And we do that with soil modeling, and as you see here in earth field dams, yes, we do that. But you need to give order to the software that this element is plane strain element.
Thank you so much, Doctor. I don't think we have any more questions, so we can end part 1 and have a short break for 5 to 10 minutes, and then we will continue after that.
Okay, thank you so much. Thank you.
Thank you.
Hi everyone, thanks and welcome back to the rest of the workshop. Am I audible?
Yes, you are.
All right, thank you so much. So, in the first part of the presentation, we covered the basic principles and knowledge that is necessary to carry out calculations in any software, structural design software. And now we'll be shifting our focus to the software SAP2000, which is said to be ideal to carry out analysis and design of any type of structural system. Dr. Batikha, could you give us an introduction to the software SAP2000?
Okay, thank you, Shirin. Thank you so much. Okay, we will continue with the second part now. Okay, and I'm going to share my screen as well. Yeah, can you see my screen?
Yes, it is visible.
Okay, okay. So after this basic knowledge, we select like SAP2000 to introduce it to you. And I believe that most of you like working on SAP2000 or you have idea about SAP2000. But before we start with SAP2000, let's give idea about the software available in market. First of all, we have two types of software. First type is high-level software, and it's for research, for doing research. Like, for example, when you heard about Abacus, it's research software. So it's not easy to be used. And if you are using this software for like simple problem, so it's not economic to be used for simple problem. So actually, we are using Abacus like when you want to introduce the nonlinearity of the material to do buckling, something like that. And ANSYS as well is a research software as well. And we have many of specific software. So Abacus is general software, the general research software you may find like in most institute, most of the research institutes. We have commercial software like SAP2000, which is general software. But again, SAP2000 or STAD-Pro, for example, these two programs are dealing with like limited number of or limited type of elements. Like, for example, I talked about many type of elements. I talked about line element. I talked about 3D element. I talked about plane strain element, plane stress element. So, and I talked about the nonlinearity of the material. So SAP2000 or STAD-Pro, it's like sometimes it's limited. It's not, it doesn't take all cases into consideration. And you may find like a software like ETABS or SAFE, for example, they are special program software for special elements. Like, for example, ETABS deal with building, but SAP2000 deal with all type of structure, like with bridges, building, soil, I mean, all type. SAFE is a program here, SAFE as well, is a program to deal with foundation. So they are specific software to be used for specific structure. But most engineers like use this software because they are easy for use. Again, this high-level software, they are for research, need like research background, like you do a dissertation and you use Abacus, or you do PhD study, or you do MSc study. So you need research background to be able to use these two software. Here, if you go to the website, CSI website, so SAP2000 and many software produced by Computer and Structure Incorporation like company. So you see that this company produce a lot of software like SAP2000, and like, for example, CSI Bridge, it's for bridge. ETABS is for building, as I said. SAFE is for foundation, and a lot of software here. So you can go and if you are interested, you can go and read about each software to see which which structure each software is dealing with. But SAP2000 is a general software, so it covers all this software together. But each software, I mean, if you want to be more specialist, so you can use each of these software. For example, if you want more specialty in designing buildings, so you can go and use ETABS. Why? Because modeling building with ETABS is more easy than using SAP2000. As well, bridge, it has like more easy way, like for example, you can like model the pre-stress in more easy way. So that's depend on the company you are working in. So it offer you like software you are using. So this is an introduction, and we are going, I mean, to introduce SAP2000 to solve many here tutorial. So I believe that it's better that we work together on this tutorial. And I'm not, I need a confirmation that you have opened your SAP2000 software and you are ready to act on. So I don't know. Everybody has SAP2000. That's, I don't know. Shirin, can you check?
Hi everyone. I'm sure all of you were asked to download SAP2000 as part of the workshop, and if you have it, could you please confirm it in the chat box once you're ready to start the presentation?
What I want to say that if you don't have SAP2000, okay, so I mean, we are going to offer you like a PDF note, small PDF note. As well, you can from this recorded video, this is recorded, will be recorded and will be available after this workshop. So you can go to SAP2000 and follow what we are going to do together. So, okay, do I?
Yes, sure. You may start the presentation, yeah.
Okay. Before I start, what I want to say that when you are using any software, so please don't go to like, don't go to try or to do example using this software using complex structure. Just use very simple structure that you know the answer of that structure to check that you are okay in using that software. And believe me that when you are succeed in doing this simple structure, so you will be succeed in doing a complex structure. So when you start using any software, don't go to do a complex structure. Because of that, you will see here that all the example I brought today are very simple. Why they are very simple? Because we know the answer of this structure. For example, if we take this simple beam, so this simple beam, we are going to model this simple beam using two types of material, steel material and concrete material. And here is the steel section as seen here. And here is the concrete section as well. And here is the load. So we have dead load, 20 kilonewton per meter, and we have a concentrated load, concentrated life load, 75 kilonewton, away from support A, 2 meters, and the span of this beam is 6 meters. So you see that this, I mean, this example is very simple example. But if you succeed in doing this example, you will be succeed in doing more complex example, more frame, as we see at the end, as we will see at the end of this presentation, of this workshop. But why we are doing that? Because we know the answer we obtain. So if you do the calculation manually, you will obtain that at the end you need to obtain a shear force equal to 156 kilonewton, and a bending moment equal to 259 kilonewton meter. So if at the end of our modeling, if we obtain these two values, so we are fine to do more example, to do more complex example. So please, when you try any software, don't go immediately to a complex example and try to do it. Do very simple example. So let's open SAP2000 together, and here is mine is ready. So this is SAP2000. You can see my screen. You still can see my screen, correct?
Yes, sir, it's clear.
Oh, okay. So here is SAP2000. I believe that all of you, all who can log into SAP2000 can see the same screen. So as a start, I'm going, as I said, to model this example. So as a start, here, we go together to file. You see that there is new model here, a command called new model. When you open this new model, you will obtain many ready models here. So you can select the most one appropriate to your model and you select it directly. Otherwise, you need to draw the model by yourself, but you can use one of these models. You see here that we have many type of model, like we have beams, we have trusses, 3D truss, 2D frame, 3D frame, wall, flat slab, and so on. So you can select any type of this model, then you do amendment to this model, like you change the position of node, you divide the model more and more. So there are many commands you can use under SAP. For my example, I'm going to select beam. So all of us, we press on beam. We will obtain this screen, and we are going to add our input. So first question is the number of span. We have one span for this beam and the length of span. We did here just one mistake we haven't noticed, so I'm going to do cancel. You see here, you see on the right bottom, there is like a box for the unit you are going to use. So now our unit we are using in kilo, pound, and feet. Okay, so we are going to change this to the unit we know. So we open this box and we select kilonewton meter. Okay, now I'm going to repeat what I have done. So file, new model, I'm going to select beam. Now, the number of span, we have one span for this beam, and the span length, as seen here in my model, it's 6 meters. So it's 6, so it's ready here. So I'm going to say, okay. So you see here that we have our beam is ready here. And this beam is one span beam. We can divide this span into many parts, by the way, by going to edit. If you go to edit, you will see a lot of command here. Like, for example, edit line, divide frame. So you can divide this frame into many frame. So you can add joint, you can add extra part. So you see that this edit offer you a lot to do as well. You can do copy, for example, replicate here. You can do move. So a lot, if you go through, we don't have that much time to go through each comment, but if you are working alone, you can try this command, and I mean, it's very easy to be used. SAP actually is easy for use. Now, I'm going, so here I have length, but I don't have section yet. Before I have section, I need to have material. So to command a material, you go to define here. In define, you can find here material. So we select material. You can select, you have two ready material here, one for concrete and one for steel, but you can add your own material. Like, for example, if I said add new material, okay, I want to start with steel, and I want to add user. Have a look. Standard, what's the standard? You can keep the standard ASTM, or you can use your own material, user material, as seen here. And I say, okay, I'm going to keep it, to call it steel. You can change the name if you want to change the name. Now, here, first of all, weight and mass. So weight per unit volume, we all know that the weight of the material, the steel material, is 77 kilonewton per meter cube. This weight will be used this weight will be added to the dead load. But if you don't want it to be added to the dead load, and you have ready dead load, like for example, in our example, this dead load 20 kilonewton per meter includes the self weight. So at that time, you can easily make this dead load 0 to avoid this 0, to avoid that you do a mistake and you add the self weight again. So at that time, if you have the ready dead load, including the self weight, and you keep this number on, so at that time, the self weight will be added twice. So to avoid that, you can make it 0. Here, you need to include E. You need to include Poisson ratio. So I'm going to change the unit again here, but inside this box to Newton millimeter. Now, according to my example, the property for steel, have a look. It's 200 gigapascal, and Fy is 350 megapascal, and Poisson ratio is 0.3. So if I go here, the elastic modulus is 200,000 megapascal. The Poisson ratio is 0.3, and here the thermal coefficient. And here the shear modulus, it will be calculated automatically, which is E over 2 bracket 1 plus mu or Poisson ratio. Here you can add Fy, but if you want to do, now here we have two things to think about. First of all, do you want to do nonlinear analysis or you want to do linear analysis? If you want to do linear elastic analysis, so this is not important. This is not important. But if you want to check the design, so you need to include it. If you want to design this. Now, first value is for Fy, and second value is Fu is for failure stress, And we know that this failure stress could be 650, for example. Okay, here the effective the effective yield stress that you need to take, it could be the same or could be lower 650. Now, when you are doing pushover analysis and you need to say to SAP2000 or to the software that the behavior of material is elastic, perfectly plastic, which means that it's the plastic zone is constant. So at that time, for the failure stress, you added the same as the yield stress. And at that time, we said, okay, don't increase the stress after you reach the yield stress. Please don't increase the stress. So you see that all this, what I'm talking about, need like understanding and background in research to know, do I increase the stress or not? Okay, for sure, if you increase the stress, if you add like bigger value here, so the capacity of your element will be more and more, because you are including here the true value. But if you assuming that your yield, I mean, you have perfect yield, and we use that in design, we assume that we have perfect yield. So at that time, you are using what we do manually to like in plastic analysis. So this is very important point here when you do plastic analysis using SAP, because in SAP2000 you can do plastic analysis, by the way. So I'm going to say okay here, but again, if you, all these parameters are not important if you are not designing your section. If you want to obtain only stresses and stresses and like you want to check the capacity of your element, or you don't want to check the capacity of your element, you need to obtain the internal force or stresses. So these fields are not needed at all. But if you want to check the capacity of your element and you want to design your element, so you need to include this parameter, Fy. So I'm going to say okay here. And you see here, after I say okay, there is a material called steel that I made it. I'm going to say okay to confirm this material again. So here, okay. Now I'm going to create section. Again, I go to define and I go to section property. Now, we have many type of element here. We have a frame element, we have tendon for pre-stress, we have cable. The property of the cable that it takes tension, but it doesn't work under compression. We have area section, we have solid section, but mainly when you are using SAP2000, you use mainly like two type of element, frame element and area element. The frame element is the line element I talked about, and the area element is the 2D element I talked about, and we are going to do example on the area element. So frame element is that I talked about in my presentation. Here the line element, or this is the line element, or two node element, and the area element is 2D element, So our element here is linear element because it's clearly as seen here that the length of this element is much bigger than the section of this element. So we go to define, we go to section property, frame section. Now here there is assumed section by SAP, but if I want to include a new section, for steel, I can import this section. So I'm going to say import a new property. Have a look. It's a steel. I section. I'm going to select I section because in my example here, if I go to the example, you see that I have here, we have here, steel section, UK beam, 356, 171, and 51. So what I'm going to do, I'm going to select I section. You see that there is like data open to me. So if I go down, you can use a section from AI, SC, SC. Here, like for example, BS shape. So I'm going to open BS shape here, and I'm going to say open. You see a lot of section, ready section open to me, hot rolled section. So I'm going to select the section I'm looking for. It's this section, you see, this section. And I'm going to say, okay. In this section, have a look, immediately, the abacus drop the size of the section, okay? You can do your own section, by the way, and you add your own size. It's not necessary that you take the same section. You can do modification to this number as well. Here, when you go to the material, you need to select the material, your materials. So have a look. If I open this arrow here, I'm going to select the steel I set for this example. So here the material is steel. So be careful not to forget to change the steel, the material for this section. I'm going to say okay now. You see that I have this type of section. So I have this type of section, and for this section, we have the material we select. I'm going to say okay. Now, have a look. If you go to this mark here at the top, you see here at the top, and you open it, and you will obtain here display options. In that display option, if you go to the frames and you ask for section, you see sections, to see what the section apply to your element and say okay, you will see that you don't have the section you created. You still have on your element the old section, F sec 1. This means that you need to assign the new section to your element. How we do that? We go to assign here. You see this command at the top, this tool at the top, assign. So we open it. This tool can assign to the element, to the joint. Like for example, you can change for joint the type of boundary condition of support. You can release or you can do a constraint for a certain joint. You can as well add section for frame. You can add loads. So this tool here, assign tool, is for adding loads, a type of frame to the element you are studying. So I'm going to assign, and I'm going to frame here, and I'm going to select frame section. So if I open frame section, you see that I have two sections here. I'm going to select my section, .ub, and I'm going to say apply. Have a look, immediately the name of the section on the screen changed to the one I want, you see? This means that now I have the correct section and the correct, support and the correct length. Now I need to apply load to my element. So have a look. I have uniformly distributed dead load, and I have concentrated life load. So how I do that? First of all, I need to open load called dead load, and another load called live load. So I go to define again, and I select load pattern. So have a look that this define tool here, define tool, is like to select something before you assign it to the element. So I'm going to select load pattern. So have a look. I'm asked. You will see automatically that you have here dead load. Here, self weight is 1. This means that you are including the self weight in this dead load. If your dead load is ready with the self weight, has self weight already, is the value of the dead load here, for example, in my example here, this 20 kilonewton per meter has already self weight. So I don't need to include a self weight. So what I do, I make it 0. And I said modify load pattern. So have a look. Now the self weight will not be available for dead load. Okay, why? Because I included already in my load. But if it's not, you can keep it 1, and you can keep the density I show you before I make it 0. When I specify the material, I define the material. So you keep that density, and at that time the software will take the self weight into consideration. Now, I'm going to add another load, and I'm going to call it live load. So this is, you can write here live, and you can select live, and as well, the self weight is 0, and you said add new load pattern. So you see here, add new load pattern. So I'm going to say add. So now I have 2 types of load. I have dead load and live load, and I'm going to say okay. Now I'm going to assign loading to my element 1 by 1. So I select the element first, and then I go to the assign tool. You see, as I said, that this assign is very important because it's to apply what you defined before to the element, to a certain element you modeling. So assign, have a look. You have joint load, you have frame load. Now I need to apply my load to the frame loading. So I go to frame loads and I select distributed. After that, have a look. First of all, which type of load you need. So be careful not to do mistakes. So load pattern, I have 20 kilonewton per meter dead load. So here I select dead, not live. And this dead load, I wanted to be to coordinate system. We have 2 types of coordinate here in any software, not just SAP2000. We have global software, which is XYZ, and we have local coordinate. So it's a coordinate belong to each element, but the global coordinate, it's a coordinate belong to joint and all elements. So it's the XYZ. Okay, what is the load direction? Have a look at the coordinate here on the screen. You see that X axis is along my element, and Z axis is perpendicular to the element. I want to apply a dead load parallel to Z axis. So I go to load direction and I select Z. Here there is already here box to uniform load, So for example, I want 20 kilonewton, but the direction of that 20 kilonewton is opposite to Z. So I add minus 10. By the way, these boxes that you can do as well, not uniform load, is for doing different from uniform load. So you can do rectangular, not rectangular, trapezoidal load. You can use this box to do triangle load, trapezoidal load. So different shape of the rectangular uniform load. But if you have ready uniform load, so you can use this one. So this box here, okay, is to introduce to your element non-uniform load. I'm going to say apply and have a look now. I have 20 kilonewton per meter as a dead load. I need as well to apply life load 75 kilonewton away from support A by 2 meters. So again, I'm going to select the element. As I see that, I select the element, so that dashed line is like is a note that you select this element. And I'm going to assign again, and I'm going to select frame load again. But now my load is point load. So I'm going to select point load. Now, the load pattern is life load. So I'm going to open and I say life load. Again, this life load, I'm going to select the global coordinate system to add this load. And again, the direction of the load is parallel to Z. Now, I need to apply this load away of the left support by 2 meters. So what do I do? Here, have a look. You have you have two ways to apply that. You use the relative distance or you use the absolute distance. I'm going to use absolute distance. What is the distance? I'm going to say 2, and 2 is 2 meters. What is the value of the load? In my example, the value of the load is 75 kilonewton. So I'm going to say minus 75 because it's opposite to Z. So I'm going to say, okay, and have a look. I have life load, have a look here at the screen. So I have life load equal to 75 kilonewton. I need to solve this example to do a combination here, So I'm going to use the Eurocode 1.35 dead load plus 1.5 life load. So I open here, define again, have a look. There is a comment in the define. It's called load combination. I'm going to open it. And I'm going to add new combination. I'm going to title this combination by the combination I know. It's better that you title the combination with the thing you know. So 1.35 dead load plus 1.5 life load. Have a look here. First case is the dead load. What the factor is 1.35. So I'm going to say add. The second load here, the load case name is life load. What is the factor for life load? The scale factor is 1.5. I'm going to say add as well. So you see that I have in this combination two loads. The dead load is 1.35 and the live one is 1.5. I'm going to say, okay. So this is the combination I have. and I'm going to say, okay. Now, everything is ready to run the analysis. I have the element, I have the load, I have material, I have section, because as I told you, you cannot run the analysis if you don't answer all these questions. So the type of element we selected is a frame element. We inserted the dimension of the element, the length and section. We select the material property. Support, we have support, and we applied load. You need to have all this data to run the analysis, and we have it. All what I'm going to do is I'm going to call it. So I'm going to save it. So save as, please don't save as directly, save it within a folder, because many sample will be open later. Many file will be open after running. So I'm going to create a folder. I'm going to say SAP2000 I-struct E. So I'm going to name this example 1. Save. So here is example 1. I'm going to run this example. This is, have a look, this is the bottom to run the example, or you can go to tool analyze and you say run analysis, or you go directly to this arrow here, sorry, this one. So if I open to run this example, you see that I have dead load, life load. The model here, you don't need to run it, because usually this is run for dynamic. So you don't have here dynamic. So you don't run it, so I press here, don't run this case. And I'm saying here, run now. So now you see here that at this screen that we have a deformation. Now let's explore our result. Manually, when we solve this example, this is the manual value. The shear force is 156 and the bending moment it's 259. So this manually. Here, as seen here, you have 3 bottom at the top. You see here these 3 bottom. The first bottom is to get back your model to its origin. So, for example, if I'm standing to the window on the left and I press this bottom, you see that the deformation, so the model get back without deformation shape and it's back to its origin. The second bottom here is to show the deformation shape. So if you press here, this bottom, you will be asked under which deformation you want to see. Usually for steel, we check the deformation under live load. So I'm going to say under live load and show me here the original wire shadow is the original shape. So show me the original shape. So if I say okay, so have a look, this is the deformation of this beam. You don't have value here. This doesn't show the value. It's because you need to show the deformation. The deformation will be shown if you have a joint. here you have only for this element 2 joint, this support and this support, but we didn't create joint at mid-span. When you create a joint at mid-span, and I'm going to show you later, you can see the deformation. Now, the bending moment and shear force. So if you go to this here, this bottom here, and you open it, and you ask for, you can go to joint, and at that time you obtain the reaction. So for example, if I go to joint, and I ask, give me the reaction under the combination, and I say, okay, so have a look. We have 156, which is the same as the shear as in the example. You see, manually, we obtain 156. So, and we can go to this command as well, frame, here, to see the internal force or the stress resultant, I call it. Again, I select the combination, and I ask, can you please show me the shear along axis, local axis 2, okay? And here is the shear diagram. You can show this diagram, you can show the value on this diagram. So if I repeat this command, if I go here to this bottom again, and I select frame, I can here have a look. There is 2 options for diagram, field diagram or show values. Show values, you see, show values. So say okay, and you will see that this is the shear diagram as expected manually. And here you see that there is a cut because you have here a concentrated load, 75 kilonewton life load. Because of that, you have a cut here. You have a change. You have a change in the diagram. And as well, if you want to see the bending moment, we go again to this bottom. We select frame and moment about 3,3. These 3,3, 1,1, 2,2 are local axis. So about 3,3, okay, and here is the bending diagram. And have a look. We have a maximum bending diagram below the load, and the value is 258. If we check our manual value, it's 259. So it's almost the same as the value from the software. So this is example 1, and I hope that you made it. So, but again, what I want to say that we are doing this simple example because I mean to practice any software. Don't immediately go to try a complex example. Always try with something you know. You know the answer manually. And by the way, always, you need to have a way to check your result manually. Always. And all students who did research know exactly that no value from a software can be accepted unless you compare this value with manual calculation. So always you need to put in your hand a manual way to be applied to check if the software, if the value given by the software correct or wrong, because you may do a user, I mean, mistake, like you do some mistake in material, you do some mistake in loading, you do some mistake in boundary condition or support. So you need always to have manual calculation, fast manual, approximate. I'm not I'm not telling you like accurate manual calculation. So this manual calculation like provide you a value within like 15% mistake, for example, between you and the software. And at that time you feel comfortable, okay, the value given by the software are reasonable. Okay, so please don't use any software without you have a manual handout calculation, like approximate. I'm not saying accurate. You cannot like achieve the accuracy as the software by using manual calculation, but you can have approximate calculation. So you need to practice how you obtain like manual, you do manual validation for the result given by the software. Okay, so this is the first example. The second example is same loading, same, but just I'm going to use like concrete section. So here, so I'm going to save this example under example 2. So I'm going just to save it. Example, I'm going to say example 2. So please save the same example under different name. Say example 2 to do some change. So I'm going to say save. I'm going to define again. I'm going to create concrete material. So add a new material. I'm going to say concrete. And I'm going to say as well user. So I'm going to say, okay, this is open, this is concrete. Again, I'm going to make the density 0 to avoid that it's inserted twice in my calculation. The unit, I'm going to change it to Newton millimeter here. In my example, the elastic modulus for concrete is 34, and the Poisson ratio is 0.2, and FCK is 35, the characteristic compressive strength. So here is 34,000. The Poisson ratio is 0.2. And this one, FC is 35. And you can keep the expected is same. Again, no needed for these two values if you would like to obtain the structural analysis, if you want to do structural analysis only. But if you want to do design or you want to do plastic analysis, so at that time you need these two values. So I'm going to say, okay, now I have concrete material as seen here, and I'm going to say, okay, I'm going to select to define a concrete section. So I go to define again, section property, frame section, I open it, and I'm going to add a new property. What is the material? I'm going to say that the material is concrete. When I say concrete, immediately have a look, there is ready section here. There is ready section. I'm going to open rectangular. The depth for this section in my example is 600 and the width is 250. So here is 0.6 meter because my unit is in meter. And here is 0.25, yes, meter again. And by the way, you can add reinforcement for this section if you want to do plastic analysis or you want to check the capacity of the section. So here there is a common concrete reinforcement. But again and again, please don't use this unless you do manual validation. So do easy example, just to be confident of what you are doing. So I'm going to say, okay, and sorry, I didn't change the name of the property here. So I'm going to say I'm going to call it con section. So have a look, I have con section here, okay. I'm going to select my element, and I'm going to assign this section to my element. So I go to assign again, frame section, and here con section, and I say, okay, and have a look, the section here is concrete section. It's not anymore steel. And I run, everything is ready. I have support, I have dimension, I have material. So I do run again. And I say run. For sure, you will have in this section, you will have same bending moment, and you will have same shear force. Why? Because it's determinate structure. But if you do undeterminate structure, for sure you will have different value. You will have different value if you have indeterminate structure. But you will have for sure different deformation. The deformation is very different here. Why? Because the moment of inertia and the material is different in the both examples. So the deformation will be different in the both examples. Okay, I believe that we may need a break here. So we finish example 1 and example 2, and the other example will be fast. So Shirin.
Sure, sir. Thank you so much for taking us through the step-by-step process of analyzing. So now we'll take a 5 minutes break again, and I hope to see you all back here. Thank you so much.
Okay, thank you.
Hi, everyone. Since the 5 minutes is up, I believe we'll be starting the presentation now. I hope everyone's joined us back. Dr. Batikha, thank you again for giving us a very in-depth explanation on how to define the material, assign loads and joins, and also understand the results given by SAP. So before we move on to the rest of the examples, Dr. Batikha, could we address a question that was left behind before?
Yeah, sure. What's the question?
Okay, sure. So Basil Ismail has asked, in the modal analysis, is it fine to have the first mode of analysis to be in torsion?
No, here when you are talking about modes, so you are talking about the modes applied during the dynamic analysis for seismic. So here it's not like it's about the configuration of the building. Actually, the modes, it's about the configuration of the building. So for example, if you have 3D buildings, so each floor will have two displacement and torsion. Okay, if your building is regular, I mean, if your building is symmetrical, for example, and you have very symmetrical distribution of the shear wall, for example, in your building, so the first mode will be a displacement mode for sure. So you cannot like enforce the software to do a torsion without doing the displacement first. The control mode is the displacement mode. So all this is study under dynamic analysis to understand what is the mode. And the third mode will be torsion. Okay, so that depends on the configuration of your building. Depend on the configuration. So if you give, for example, if you give eccentricity to your building because you applied the load, the seismic load, you applied at the center of the area. So if you give eccentricity, you may enforce the software to do the torsion first. So that depends on the configuration of your building. I hope this answer.
Yeah. Sure, that was really clear. Thank you so much, Batikha. And now we'll be moving on to the rest of the examples.
Okay. So let's go. I'm going to share my screen again. So you can see my screen again. So I'm going to example 3, which as seen here, that it's simply supported one-way slab. And you see that it's the dimension of this slab is 4 meter, 2 meter, and I supported from 2 edge only to confirm that this slab acts as one-way slab. Okay, otherwise the slab, whatever the dimension of the slab will act as two-way slab, and you will not know if your answer is correct or not. So please, that's the aim of this simple example, just that you know manually, if you solve this slab under this load, here is the material property, here is the section, here is the load, here is the combination, and the answer, the final answer, if you do it manually, here is the final answer. So I'm going to work on this example very fast, and in this time, I'm going to use area element. So let's go here. So I'm going to open new model again. So here is file, new model. I'm going to select wall, This is ready. Now, for this wall, you are going to be asked about the dimension in X direction and in Z direction. In X direction, and how many division you need here. Here, the division is very, very important if you are doing nonlinear analysis. But it's not that important if you are doing elastic analysis, but you need to do division. But actually, when you are doing nonlinear analysis, we ask the researcher or the student to do something, we call it mesh convergence, to confirm that this division is correct and can provide accurate result. That when you are doing nonlinear analysis, but in our example, we are going to do linear analysis. So for example, we have here 4 meter lengths in X direction. I'm going to divide this into 8 distance, which means that's 50 centimeter or 0.5 meter for each division. So I have here 8 division, and each division is half meter. In the Z direction, I have 2 meter dimension. Have a look, 2 meter dimension. I'm going to keep the division of half meter in Z direction as well, which means that in Z direction, I'm going to divide this slab into 4 division. So if I go here, I'm going to say 4, and the division in Z direction, the distance, the division width is half meter again. So I'm going to say, okay. So have a look. Here we have a slab. But have a look at this slab. Because I select here a wall, so the support only down. Have a look. At bottom, we have support. So we need to change this support. So I'm going to select this support, this edge. Have a look, the node selected. I'm going to select as well the top edge because I have support at top and bottom. And I'm going to change this support. How do I do that? I go to assign, then joint, restrain. In this restrain, you can select the support you want, or you can add the support manually. Like for example, if you select pin support here, have a look. This means that you prevent the deformation in 3 directions. But actually, if you apply this pin support, you may have axial force when this slab deforms. Because of that, I'm going to order the program that I have only please or restrain this slab against Y direction, out of plane direction. Have a look before at the coordinate here. You see the coordinate that I have coordinate X and Z in plane, but out of plane here is Y axis. So I'm going to say, please restrain the deformation in Y direction, or in plane direction, out of plane direction. So I'm going to say, okay. So now have a look, the support change. It's not fixed support anymore at the bottom direction. So it's in Y direction. Again, I'm going to give material to define material and section. So define, I'm going to do fast this step. So define material. I'm going to say add new material, and I'm going to select concrete. And I'm going to add user material. I'm going to say, okay. So this is concrete material. I'm going to say for the density 0, because I already include the self-weight into the load here. And I'm going to add the properties of the material. So here, Newton millimeter. So here, have a look. This is the property of the material. E is 34, FCK is 35, and Poisson ratio is 0.2. So here is 34,000, 0.2, and here is 35 megapascal for FCK. I'm going to say, okay, so I have concrete material now. Okay. Now I'm going to define a section for this area. So I'm going to define section property, area section. Have a look, area section. Open. It's shell section. I'm going to add new section. I'm going to give it a name. I'm going to say that this is a slab. Have a look how many section you have, type, how many type you have. First of all, you have shell thin. And I talked about this thin. I said that this thin is the plane stress. Sorry. Here, when I explain the plane stress, this means that this shell is thin, which means that the thickness of this shell is very small. It's like, let's say, is from term like 1/10 the dimension of the slab. So for example, if this slab here in our example, this slab is the minimum dimension or the short direction is 2 meters. If we take 1/10 or 1/20, for example, so this means that this slab is 100 millimeter. So this slab is for sure thin slab, but the thick slab is that what I talked about, that plane strain, where you consider the shear deformation. So plane strain, that the thick slab. So here you select shell thin or shell thick. When you select plate, so this means again that this usually for like steel, and it's from the name, it's a plate, so the stress as well is it's act not in Z direction, doesn't act in Z direction. Membrane here is very important. It's for domes, this membrane. When you select membrane, this means that in membrane structure, like here, membrane structure like Sydney here in my screen, like Sydney Opera, or here mosque domes. So you don't allow a bending moment to appear. So only you have axial force. You have two types of axial force. You have a force along the dome, along to the surface, to the vertical surface, or the circumferential of the dome here. So you have only force. You don't have bending moment when you design dome. And because of that, if you don't allow the bending moment to form in this slab, this means that the force, the axial force, will be bigger than usual. So because of that, your design is safe here. But you order the software that this is a membrane. So please just give me force, axial force. Don't give me bending moment. So for our slab, we are going to select shell thin. So actually shell is the general element. As well, in all software, you have general element and you have special element. So when you select shell, So as you shall select general element. But again, if you have DOMs, you are doing to study DOMs, so select membrane. But the plate rarely to be used, plate element. So shell is more general. Now the thickness, in my example, the thickness is 100 millimeter or 0.1 meter. And the material is concrete. I selected, so, and I'm going to say, okay. So I have now this element and I'm going to say, okay. I'm going to select the element here in my screen and I'm going to assign this section to this element. So have a look, assign area, because I'm dealing with area, sections, slab. I say okay and have a look. All the elements here have slab section with concrete material. Now I'm going to apply load. Again, I'm going to define and I'm going to open load pattern. Dead load, I'm going to make the self load 0 here. And I'm going to do life load. We did that before. So life, and I'm going to add new load pattern. And I'm going to say, okay. Now, what do I have in this example? We have dead load. We have dead load 3 and life load 2. But actually, we need to add here the self weight here itself. The self weight, we have 0.1 thickness. And we know that the density of the concrete is 25 kilonewton per meter cube. So 0.1 times 25, we obtain that we have a self weight. It's 2.5 plus 3. So we have a total dead load 5.5 kilonewton per meter square. So I'm going to select this element and I'm going to say assign, now add area load. What do I need to add? I need to add uniform. So here uniform, I need to add dead load, global. Now, this load is parallel to y-axis, as seen from the draw. And I'm going to say here 5.5 because the self weight and the service load, the total is 5.5 kilonewton per meter square. So I'm going to say okay. So now I have dead load 5.5. I'm going to select it again to add the life load. So here, select this, assign area load, uniform again. Now I'm going to select life, and the life load is parallel to y-axis as well. But the life load this time is 2 kilonewton per meter square. So I'm going to say 2 here. And okay. So now I have dead load, I have life load, and I'm going to add combination. So I go to define long load combination. We did it in example 1. Add a new combination. I'm going to say 1.35 dead load plus 1.5 life load. And I'm going this to this load. For dead load, the scale factor is 1.35. I'm going to say add. For the life load, it's the scale factor is 1.5, and I'm going to say add as well. So here is my combination is ready. I'm going to say okay, okay. Now everything is ready. I'm going to save this file. Save as example 3. I'm going to call it example 3. And it's ready to be run. Everything is ready. Support, dimension, element type, material, everything is ready. So I'm going to run it again. For the model, I'm not going to run it because we run it if we have modes shape. We don't have it here. So run. You see that's how we have deformation in this slab. Now I'm going to explore the bending moment. You see here, it's assumed that the bending moment equal to 5.2 and the stress 3.12. So I go to this bottom, I open it, shell, have a look, shell. And here, resultant force. I have for the local axis. I'm going to explore the local axis for this element. So have a look. If I open here, have a look this at the top, this mark. I go to area and I ask for local axis and I say okay. So you will see that you have this local axis for each element. The red one is axis 1,1. The green one is axis 2,2, and the blue one is axis 3. So I need the bending moment at axis 2,2. So I'm going to open here and shell section, and I need bending moment M22. And I'm going to say okay, and have a look that the value here is 2.86, or yes, the maximum value is 2.86. So in our example, it's assumed, sorry. Here you see that this value is for dead load, so I need to change the combination. I need here to select here the combination 1.35, 1.55, 1.5 live load, and M22. And now I have the same answer as manually obtained. Have a look. Now, I said earlier that to know how this slab crack, you need to obtain the principal stresses. So here, it's the unique here. So we open here, we go to shell, we ask for shell stresses, and we ask for S max. Actually, S max is the principal stresses, the maximum principal stress that I call it sigma 1. If you remember in my, when I showed you the Mohr circle here, I said that there is sigma 1, there is sigma 2. This is the principal stress corresponding to tau equal to 0. And this gave you in concrete the failure shape. So if we go here and we ask for S max, S minimum, SVM, this SVM is von Mises. von Mises. You don't use it. You don't use von Mises unless you have steel member to check if that steel material yield. Here, so S11 is the stress in direction 1. S22 is the stress in direction 2, axial stress. S12 is the shear stress. S max, the maximum principal stress. S minimum, the minimum principal stress. SVM, the von Mises. S13, S1, S23 are the shear stress, but here it's thin plate, so you will not obtain shear stress. SV max is the principal shear stress. Principal shear stress. But actually to find the crack, you need S max or S minimum. So let's go with S max, apply. And this is how this is the visible. Okay, so here I'm going just to change the unit. So here is the stress, and here is, you see that the concentration, actually this not shown because I need to show the bottom face. Here is minimum. Okay, here, have a look at this shape. You see here that at the center of this slab, you have here like line. You have like here, have a look. You have like line. Because of that, the one-way slab cut into two at that line. And this is, by the way, the direction of the crack appear in this one-way slab. Have a look, and have a look at the variation of this contour. So it goes, the maximum will be at the center, then it goes slowly, I mean reduce slowly until you reach the support. But have a look, the concentration of this contour is at the center, and it's drawn at the line, and I'm going to show you now this line. So please have a look here. This line, you see this line? This is the crack line, how the slab crack. So this is the example, 3. I'm going to change, I'm going to deal with the same plate, with the same slab, but I'm going just to change the boundary condition. So I'm going to make it two-way slab, exactly as example 4. So now this slab is supported from 4 edge. Just to see what's the change. It has the same material, it has the same force applied, the same combination. So I'm going to save this example. I'm going to save it under example 4. And I'm going just to add here, you see here, these two sides, this node at these two edges. I'm going to support them. Previously, they weren't supported. I'm going to support. So I go to assign, join, restrain. Again, I'm going to say, please restrain this joint against the Y movement. I'm going to say, okay, and you see that now all 4 edges are restrained. I'm going to run this example. It's very good to see what the difference now. So have a look at this change. This again, this is the, again, it's the principal stress. So have a look at the shape here. It's go like from the center here and go reduced until it reached the corner of the slab. I'm going just to show you here. Have a look at this black line come from the contour of the principal stress. And I believe that you are very familiar with this line. So this slab, when you support from 4 edge, it acts now as two-way slab. And the transfer of the loading to the edge come through 4 regions, trapezoidal and triangle. And I mean, we deliver at Heriot what we deliver, or I deliver a course about plastic analysis, and we deliver a title called Yield Line Design. And to obtain the yield line design, you need to order SAP2000 like here. You need to order it. Please give me, provide me the principal stress. Here, another example about like opening. You can do same example. I'm not going through this example because it takes time. So you can model, and after that you can remove actually this, you can remove this opening. But have a look, what I want to say is to look at the principal stress again here, the principal stress. So have a look. You will find that there is concentration at the corner of the opening. After that, have a look how there is like a line here between this corner and this corner. Have a look at the contour. Have a look at the contour as you do a line. This gives you how this slab cracked. If you compare between this model and the real model here in the experiment, you will see that in the experiment you obtain the same direction of slab, of cracks as the software provides you. Have a look. So that's what I said, that if you want to know how the slab crack, you need to ask for principal stress. This is very useful because if you want to strengthen this slab, you need to know how the crack happen in this slab to add reinforcement or to add steel member or to add FRP, like for example, fiber reinforced polymer. Because if you know this crack, you do a reinforcement perpendicular or cross this crack at that time, you strengthen this slab. So this is very important. I'm going to example 6. In example 6, we are going to do 2D frame. 2D frame. So here is a frame. Here is the element of that frame. So we have column, we have beam, and here is the plan view of our building. And I'm going to select, and this example is symmetrical. So I'm going to select one frame and study one frame. So I'm going to select frame 1 and study one frame. And as seen here, that this building is under a seismic load. So at floor 1 or at first floor, we have 10 kilonewton applied to the whole building, and at second floor, we have 20 kilonewton applied to that building. So I'm going to model one frame. So here is, I'm going to open new model. Have a look. You have here a ready comment. It's called 2D frame. 2D frame. First of all, I'm going to change the unit here to kilonewton meter. And I'm going to file new model 2D frame. So I select 2D frame. There is some question you need to answer. So what is the number of story? You have 2. Number of bays, you have 1 base only. What is the story height? You have 3. What is the bay width? You see in the example that it's 5 meter, the bay width, it's 5 meter. So it's 5, and we say, okay, and here is our frame. I'm going to change the support. So I'm going to mark just the joint, and instead they are pin joint. I'm going to assign and change the restraint to fixed joint. So you can press this button and immediately you obtain fixed joint. So no translation, no rotation. So I say, okay, so now you have fixed joint. I'm going to select to define material and section. So define material. We have here steel material as seen here. So add new material. I'm going to select user material, standard user, okay. For self weight, I'm going to say that it's 0. And I'm going to change the unit to add the properties of the material. The elastic modulus is 200,000 and the Poisson ratio is 0.3. And again, here, I'm not going to change this because I'm not going to do design. So it doesn't matter. So or nonlinear analysis. So it's okay. So this is the steel material and here is okay. I'm going to select section. Actually, for this frame, I need 2 sections, 1 for column and 1 for beam. For column, you see that the section is UK column 152, 152, 23. So I'm going to select section, frame section, import new property, I section, and I'm going, as I did in example 1, I'm going to BS shape, and I'm going to select UC 152, 152, 23. So this okay. Again, don't forget to select the right material. So you open here and you say that this is steel. You said okay, and you have UK U column. I'm going to select a section for beam. Again, my beam here in the example is UK beam 178, 102, 19. So I need this section. I'm going to say okay, and don't forget that the material is steel material. Okay, so I have 2 sections. I'm going to say okay. For the column, I'm going to select the column as seen here. And I'm going to assign frame section for the column. I'm going to assign this section to the column. So have a look. I have the correct section. For the beam, I'm going to select the beam and I'm going to assign section for this beam. So here is U beam. So my model is ready with section, with material, with support. I need to add force. What is the force I need to add? As seen here, at first floor, I have 10 kilonewton, but this 10 kilonewton will be divided into 2 for each frame. I have 2 frame 1, 2 frame 1. So actually at 1 frame, we have 5 kilonewton at first floor, and we have 10 kilonewton at the top floor. So I'm going here to select this joint. Now I'm going to apply a force at a joint, not at a member. So this joint, and I go to assign joint load, but I didn't define the load yet. So I go to define here, load pattern. I say seismic. The type is earthquake and no self-weight required. So add new pattern, seismic. I say, okay. Now I go to the joint here. I select this joint. I go to assign joint load because it's joint load, force. This load will be parallel to x-axis, so it's 5 kilonewton. We agree that the 10 kilonewton we divided into 2 because we have 2 frames, so 5, and I say apply. Okay. The top will have 10 kilonewton because we have 20, but divided into 2 because we have 2 frames. So assign joint force, and it's parallel to x-axis, and the value is 10. So here is the force applied to this frame. I'm going to save this example under name example. I'm going to call it example 6, as in the presentation. So I'm going to say okay, and I'm going to solve it. It's ready. I don't need in this example to solve the dead load, so I'm not going to run it, and not the model load. I need only the seismic. I need to run the seismic, and I'm not going to do any combination here. So run. So now have a look. First of all, let's do the deform shape. So I'm going to select here deform, and I'm going to select seismic, and I'm going to say apply. Sorry. Sorry. Sorry, I did a mistake, I believe, by applying loads. So this point frame load, sorry, joint load force, I did a mistake that I didn't take seismic here. So I need to apply this 5 kilonewton to seismic case. So I did a mistake that I didn't change the load pattern. So I'm going to say okay. And here as well, sorry for this mistake, joint load force, and this is 10, and okay, and I'm going to run it. So you need to be careful with that. So you see now we have a deformation. If you stand at the joint here, if you ask for deformation for seismic, and you stand at the joint, you will be given the deformation value. So this is telling you that the deformation value in U1 in x-axis, in x direction, is 0.0136 meter, because the unit is in meter, and the top story is 0.0291. Now, if I want to explore the force, like for example, the bending moment. So here I go to this bottom, and I select frame. For seismic, I select moment 3.3, okay, and have a look. This is the shape of the seismic of the frame, of the bending diagram for a frame under seismic action. Okay, so this is how we model 2D frame. I'm not sure if we have time to take the third. It's a 3D frame. So I'm not sure because we almost about the time of this workshop. So Shirin, what do you think?
I believe we can go through it really quickly.
I can stay, by the way, I'm ready. If everybody is happy, so I don't mind. So do I go?
Yeah, sure. If we can cover it really quickly, we'll have this one too.
Okay,
We
so
haven't received a lot of
I need further 15 minutes. It's fine?
Let me just check 1 second. Yes, sir, please continue. Yeah.
Okay, okay. Yeah. Okay, so this is actually important example here because I'm going to teach you now how you do diaphragm. And I'm going to solve this example as 3-dimension example. So here, I'm going to open as well, new model. We are going to select now 3D frame, 3D frame. Okay, so let's open it. How many number of story we have? We have 2 story. How many number of pay in X direction? We have 1 pay. And in Y direction, we have 1 pay as well. The story height is 3, but the pay is 5 in each direction. So I'm going to say, okay. So now as seen here that we have here this frame, 3D frame, and I'm going as well to change the boundary conditions. So they are simply support. So I'm going to mark 3 of them. By the way, if you see these 2 arrows here at the top, have a look at the top. You can go now level by level. So you see this is level 1. Have a look at the left window and to the right window. And this is level, the upper level. If I want to go down again, I go to this arrow to move down. So I go to the lower level and now to the foundation. So by this way, you can go level by level and you select the change you would like to make. So I'm going to select the boundary condition. Then I do assign frame, joint, restrain, and I'm going to say fixed support. So this is okay. Now I'm not going to select for you material or frame. I have a name of this example, or let's do it fast. Okay, for the material, add new material, steel, user, okay. And here for the density is 0, and I'm going to select this as 200,000, and this is 0.3, and I say, okay, so I have steel material. And I'm going to define section property. Again, for column, we have here BS shape, hot rolled section, so open. And I'm going to select UC 152.152.23. So here it is. And the material, don't forget to select steel and say OK. And I'm going to select my beam. So again, here is a beam, and this is the section for my beam, and I'm going to say OK. Don't forget to select the correct material, steel, OK, and here is OK. I'm going to assign the section to my model. So I'm going up to first floor, and I'm going to mark to select my beam. And I'm going to say, and I'm going to upper floor, and I'm going to select my beam. Have a look. Have a look at the left side, the left window. That's 8 beams selected. 8 beams selected. I'm going to assign a section for these 8 beams. This is U beam, okay, and now they are selected. I still need to select the column section. Let's have a look. What's the type of the column section here? If I go to this mark again and I order sub to give me the frame section, so have a look. The type of frame section is FSEC1. Instead, I select the column one by one. I can go to select command. Have a look at the top, select command. I go and say select. I go, to property, and I say frame section. So please, I'm going to ask SAP2000 to select all the section which has FSEC1. Select, have a look. The column are selected. I'm going to assign section for this column. So this is frame section. This is column. Okay, that's it. So I have now this frame, 3D frame. I'm going to define a load pattern. Again, I don't care about the dead load. I'm going to apply seismic only. And the self weight is 0 here. So I'm going to say add new, sorry, not dead, sorry, it's quick. So I'm going to add, to say modify the size. So I have now a seismic load type. I'm going to say, okay. Now, how do I apply seismic? And here is very important. So I have 2 force, 10 kilonewton at lower level and 20 kilonewton at the upper level, apply to the whole building. It's not for a certain frame. It's applied to the whole building. Where do I apply this force? Actually, I apply it to the center of the slab, to the center of the slab. So I'm going to create slab here. Have a look what I'm going to do. I'm going to draw. First of all, I'm going, yes, I am in the top level. I am in the top level. Have a look. I'm going to draw, and I'm going to draw area. Draw rectangular area. So I go and select this point and this point. So we have here area. You see what we have? And I'm going down as well to the down level. And I'm going as well to select draw and draw rectangular area. And I'm going to draw area here. So have a look, I have area for each floor at each floor. I need to divide this area. Why? I'm going to tell you why I need to divide this area. Because I need to apply the load at the center of this area. So I'm going to divide this area into like 4 divisions. So I go to edit area, have a look, divide area. Here like 2, 2, it's fine for me. So I say okay and have a look. The area is divided. I need a property for this area. I go to define material. I'm going to select concrete very fast. User, okay. This is concrete. The weight is 0. And the material, I'm going to select a material. So E modulus is 34,000 as I did. And I don't care about this 35 because I'm not going to design. So it's okay. So here is the material. And I'm going to define section for this area. So define section property, area section, and I'm going to add a new section, and I'm going to select shell's thickness. I'm going to say slab, again, to call it slab. And the thickness is 0.1, 10 centimeter for this slab. And the material, again, is concrete. Don't forget to add the correct material. I'm going to say okay, okay. I'm going to select this area and at the top as well. And I'm going to assign area, section, and select slab. Now here you have 2 options actually. You can add the seismic force directly to this point because this point is the center of the area. Always when we apply the lateral load, we apply it to the center of the area. And the SAP2000 or any other software will distribute this work to the lateral resisting system. But I'm going to teach you a new command, which is diaphragm command, which is very important command. So now I am in the lower level. I'm going to mark all these nodes. Have a look. I mark all these nodes and I go to assign joint constraint, constraint. Define joint constraint, I'm going to say diaphragm. What is the meaning of diaphragm? The meaning of diaphragm in earthquake that you have here a rigid slab which can confirm that all vertical element connected to this diaphragm can deform like uniformly. Okay, so the diaphragm, the rigid diaphragm, confirm that all the vertical elements move or deform uniformly. Okay, so I'm going to say okay, and I'm going to say apply. So all this point now has a diaphragm. And I'm going to the upper level and I'm going to mark this joint. And I'm going to say assign, join again, constraint. And I'm going to say diaphragm again. sorry, add a new constraint, diaphragm. I need this, I didn't, sorry, I didn't add because, so diaphragm 1, I need this diaphragm to act along axis X. I say, okay, I say, okay. So now I have diaphragm. I'm going to the bottom level again, because I didn't say apply to the diaphragm. So selected assign, join, constraint, and define join constraint, diaphragm again, add a new diaphragm. So this again against x-axis. So all the element, the deformation along x-axis will be same or uniform. So here, okay, okay, and this apply diaphragm to, sorry, this, have a look how all these joints are combined together, and I'm going up again and say like this, assign join, constraint, diaphragm 1, apply. So here we have diaphragm. What I'm going to do now, I'm going to the bottom level, I'm going to select this node, and I'm going to add joint load force in X direction, which is 10, the total load, the total load. Previously, when I did 2D frame, I divide this load into 2. Now I'm going to apply the total load, 10. So have a look. I'm going up to the upper level. I'm going to select this point, and I hope that I assign this total load to seismic. Yes, seismic. So it's a 20 kilonewton. Again, I'm going to say apply. So we have now seismic. Everything is ready. So what I'm going to do, I'm going to save this. And I'm going to say this is example 7. And I'm going to run this example. I don't need to run the dead load and no need to run the model. So only seismic run. And here is, you see the deformation on the left side. If I want to take on the right side, if I want to take the view, like for example, let's take XZ view. So here is the frame. And if you compare, by the way, this bending diagram with example 2, with example 6, we solve 2D frame, you will see that's almost the same value for the bending moment you obtain. Okay, so this is how we do like 3D model. Again, these examples are simple examples, but there is a purpose of this example. It's like to start dealing with a software. So please, please don't go ahead to a software and do complex example. Always start with simple example that you know the answer manually. Okay, and don't start with something mystery for you. Do something you know first for practicing. After that, with full confidence, you can do a complex example. So that's all the example we have for today. Thank you.
Thank you so much, Dr. Batikha, for the very insightful session. And I hope everyone's been following the presentation so far and trying to do the examples yourself at home, because it was definitely really helpful. Now we'll be moving on to the Q&A session. And so if you have any questions, please do send them to us using the Q&A feature of Zoom, or on live stream in YouTube. And we'll have Hawain to handle the questions, please.
Okay, so of course, as Sharon said, can go ahead and use the Q&A feature of Zoom. And also to our attendees on YouTube, you can also ask questions there. We'll be monitoring the chat there as well. So feel free to ask questions. Okay, Tanvir Khan is asking if we can get the slides. The slides will be made available.
The slide, I can offer the slide. Yes, I'm happy to offer the slide. And as I said as well, that I can offer as well the PDF notes about SAP2000. Yeah, no problem.
Someone on YouTube is saying, can you share your Gmail address? They need help with assigning a tuned mass damper.
Yes, actually, I added in the slide in the presentation here. I add my university email, so he doesn't need my Gmail email. It's my secret.
Okay.
Okay, so he can drop me an email on my here you what email, and I'm happy to answer.
Okay, Mohammed is asking that they're asking about the cable structure as per your experience. Is there or will there be a figurable difference between the manual and SAP2000?
No, for sure, there will be no different. And again, as I'm saying, and as I confirmed many times, that when you do cable structure, you can do simple example of cable. And actually, we have a lot of example in our course, in one of my course, like plastic analysis of structure about the cable structure. So you can do simple, and you know that the cable only take tension. It doesn't take a compression. So when you define a member as a cable in SAP2000 or any software, so you expect that that member will take tension only.
Okay. Any other questions? If you do have questions and it's taken quite some time to write, you can raise your hand and we'll allow you to speak directly to Dr. Mustafa. Okay, then I think that concludes our night for today. Just want to say thank you to Dr. Mustafa for taking the time out to come to us to carry out this workshop. You know, I think we learned a lot today. If anything, you know, you stressed a lot of times the importance of the manual validation to ensure that our model is correct. Also, we also looked at having to have the data that we require before we go into modeling for SAP. So for example, the element types, the dimensions, the material behavior, as well as the supports and the applied load that we're going to be using. And we looked at how to apply those in SAP based on the models that we're analyzing. And today in the models that we analyzed, you know, we looked at the simply supported beam, look at 1- and 2-way slabs, as well as 2-dimensional and 3-dimensional frames, as well as how to implement the diaphragm command. Now I feel like I can speak for everyone that we're grateful for what you've done for us today. I feel like, if anything, everyone here can go home with something that we've learned. And yeah, we just want to thank you again for being here and taking the time out to teach us today. Also, if towards our audience, if you need the slides as well as the PDF that Dr. Batikha was speaking about, you can get those from our Instagram page. And I'll just put the details of how you can contact us if you need any other information about that on your screen. Just give me 1 second. So yes, you can see our contact details. So as I said before, the PDF as well as the slides will be available on our Instagram page. You can also email us at istruct.ymg.uae@gmail.com. And then you can also contact us through the website where you get basically the same email address. And then this lecture, this workshop is recorded on YouTube. So if you can go back and watch the workshop afterwards, just to brush up on some things. So yeah, that concludes everything. Thank you all for being here, and good night.
Good night, all. Good night. Good night, and thank you all. Have a good meal with Talabat.